Why are all the YouTube videos on Ford focusing? This crap isn't even polylog. Okay, so this is just a very quick, non-systematic review of the Webflow minimum cut algorithm that I learned in the XYZ summer camp. I just felt like if I don't review it for too long, I'm just gonna forget about it. So here it is. I didn't really write a summary for this algorithm yet. I'm just really thinking off the top of my head and with a little help from the XYZ presentation slides. Anyways, so first of all, let's explain what the Webflow and minimum cut algorithm does. Basically, you have a graph, just like we do in every graph theory problem. However, this time, the graph is more like a system of connected pipes in which you can imagine something like water or gas or whatever is flowing through them, and each pipe is an edge, and each edge or pipe has a maximum flow that can flow through this specific pipe. For example, in this situation, say this pipe marked with a 5 with the arrow to the left means it's a pipe that goes from this node to this node, and you can have at most 5 units of water or gas or whatever flowing through this. And on this graph, there's two nodes, the S node, which marks the source, and the T node. I'll use a different color. The T node, which marks the termination, or I don't know. I don't really know what it means, but like we usually use S and T. Anyways, we're trying to find the maximum flow through this graph, meaning the maximum units of water or gas, whatever, flowing through this graph from S to T, and you're trying to find at most how many units can flow from S to T. And there is a few theorems that we have to go through first before we start anything. So, for example, the first and most important theorem, we can't really talk about that yet. We first have to learn another important concept in max flow, and that is the minimum cut. So, any cut in this graph is, say, this is a cut. Any cut in this graph is a line, you can imagine it, that divides this graph into two parts. So to the left of this purple line is S, and to the right is the supplement of S. And as you can guess, S and supplement of S add up to the entire graph. And doing this, we divided the graph into two completely separate parts, and the value of this cut is defined by all the edges that flow from S to the supplement of S. So in this case, the value of this cut is 10. Why not 15? Because this 5 is not added as it's flowing backwards. However, if we do the cut at a different spot, say we do it right here, then the cost is going to be this 4 edge plus this 3 edge plus this 2 edge, which is going to be a total of 9. So the value of this cut is 9. The first important theorem of max flow is the maximum flow equals the minimum cut. Maximum flow, as we've already defined, is just the maximum units of liquid that can flow from S to T flowing through these pipes without exceeding the limit of any pipe. And the minimum cut is the cut with the least value, pretty obviously, right? So for example, in this case, we can try a few different cuts and we can discover the minimum cut is going to be this one, the one that we just did with, no, actually, hold up. I believe it's going to be okay, actually several cuts are tied for the minimum, but for example, this one is a minimum cut with a value of 9. So the units of liquid that can flow from S to T, the maximum units of liquid that can flow from S to T is the minimum cut, which is 9 units. And how do we know this is right? Well, this is actually kind of intuitive. First of all, we can know that the max flow must be less than or equal to the min cut, right? At least. Because if you think about it, the minimum cut is the smallest out of any cut, which means whatever path the maximum flow takes, or well, there could be multiple. So for example, in this graph, we can mark the maximum flow first. We have a flow of 5 to over here, and then one of them goes up, 4 of them goes this way, and then this one flow that went up, along with 4 units that went from this way, can be distributed because they add up to 5, right? They can be distributed among these two with a total flow also of 5. So 2 units go this way, 3 units go this way, right? And then the 2 units, obviously they can't go this way because this pipe is backwards. So you have to go down this path, another 2 units. That's the 2 unit that came from this pipe, right? And then those 2 and 3 along with this 4 units come over here, and that's going to be a flow of 9. And then these 9 go through this last pipe to reach T, and then the maximum flow has been found, and it is 9. And as we can see in this graph, the maximum flow is indeed equal to the minimum cut. But how do we prove that this is right for any graph? Well, now that we've marked the maximum flow, it's kind of complicated. I'm just going to delete all of that. Why is it always less than or equal to the minimum cut? Well, the minimum cut is any separation of the graph into 2 parts, which means however the maximum flow goes is going to be some kind of a few sequence of edges connecting from S to T, and these edges must be cut in 2 halves by some cut. That cut might not necessarily be the minimum cut, or it might be. And there's going to be one of these, and every single one of these cuts is the sum of the flow of the cutted edge. So in this case, well, I'm not really even drawing on the graph anymore, but it's just these 3 spots, right? That's been cut by the minimum cut, and say the maximum flow is these 3 brown lines. And we know that any spot on these 3 brown lines, any cut, the minimum one out of any cut is going to be the maximum flow, because we'll say in this entire front section you had a flow of 1,000, but at this spot you only have the pipe can only let 10 units of water go through. So this 1,000, the 990 of them is wasted because only 10 units can go through at this bottleneck. So you can kind of think of the minimum cut as a bottleneck effect. I finally found the right metaphor for it. Okay, now that we understood why the maximum flow is always less than or equal to the minimum cut, it's also easy to understand why it's actually equal to instead of less than or equal to. And I don't really know how to strictly prove that. I mean, we learned it in XYD, but I don't really remember. Anyways, now we know the maximum flow is equal to the minimum cut. I'm actually going to leave this on here because it's going to be quite important. And now, how do we find the maximum flow or minimum cut? Well, now we're going to introduce the first algorithm, and it's called the Ford-Fulkerson marking algorithm, and also known as FF. It is one of the least efficient, I believe, maximum flow or minimum cut algorithms. And there's actually 3 of them that we're going to learn today, and the Ford-Fulkerson is the most straightforward and simple. Okay, so where's my drawing board? Okay, these pictures are all XYD pictures that I just copied and pasted off of their PPT, their slide, and yeah, all rights reserved to XYD in case they sue me, which they probably won't because I have 30 subscribers. Anyways, so let's start from a graph like this. So notice that to find the maximum flow, we're essentially always finding a path that is not full, right? This is kind of easy to understand. If we go back to this graph, say on this path, which technically can allow at most 4 units of water, right? Because the minimum cut of this graph, of this edge, this path is 4. So technically it can allow 4 units of water to flow through. However, if currently we're only having 2 units of water flowing through this edge, and obviously we still have 2 units of water to spare, and that is going to be known as a, hold up, let me search up the word, increased flow path. Yeah, that's probably a pretty direct translation, but that is what Google Translate called it, and that's what we're going to go with. This is an increased flow path with an increased capacity of 2, because currently we're only having a flow of 2, but this path can have at most 4. So essentially, Ford-Fulkerson is just an algorithm that repeatedly finds an increased flow path. In this graph, this is the first increased flow path, and then we have a second one, and there's a bunch of other over there, and we're just going to look at the first one for now. Notice that the way this graph is marked is the number on the left of each parenthesis is the maximum flow allowed on each pipe, and the number on the right is the current flow going through this pipe or edge. And as you can see, at first, all the pipes have a current flow of 0, 0, and after the first increased flow path is found, some of them have a flow of 2 now, right? So as you can see, this edge has just became an increased flow edge of 2 because we realized that the bottleneck on this edge is 2, and therefore this edge can increase the flow by at most 2. And we also mark on each point. This is why the forward focusing is called the maximum flow marking algorithm, because you have to mark every node and mark where the increased flow came from. And if there's a plus sign, that means it came from a forward edge, and the letter before it represents whichever point it came from. In this case, it's S plus, meaning a forward edge increased the flow by 3 over here. And so for B, it's A minus. Wait, hold up. Why is it A minus? Hold up. I think I'm covering something up. These are all forward edges. Okay, I don't really know. I think it might be a typo, but technically the increased flow should have came from A plus. I believe it should be a typo here. Maybe I'm wrong. Okay. Anyways, the forward focusing algorithm is pretty brute force and straightforward. You can look at these graphs a few more times if you want, but basically you just continuously seek if there's any path that is not full in flow yet. And yeah, it's pretty brute force, and it's not polylog algorithm, I believe, because when there's rational number edge weights instead of integers, the process might continue going forever. Anyways, this is the forward focusing marking algorithm, and it's pretty useless. We probably will never use it because it's not polylog. And now we can, okay, first of all, we still got to like briefly review like essentially what this does. So essentially, you just brute force over every single path from S to T and see if it's an increased flow path, as in if every single edge on this path has a flow that is not yet its capacity. And now let's look at the second algorithm, also known as, hold on, I'm scrolling down, also known as the, here, Edmond-Karp algorithm, or we just call it EK. So EK algorithm is different from FF, but it's basically just a slightly improved version in which we don't just find any path to check whether it's increased flow. This time we run a BFS first, and then we always use the shortest path and see if it's the increased flow path. How is the shortest path found? Well, right now we treat each edge as a weight of 1. So the edge weight is not determined by the capacity, rather is a non-weighted graph, and each edge has a weight of 1. And every time we just use the shortest path. And this time it's finally polylog, and it's provable that EK has a time complexity of nm squared, in which n is the number of nodes and m is the number of edges, nm squared. So if you want to prove that, you can. I didn't really, because we didn't have much time in the camp, and we just jumped straight to an important algorithm, which is Dinic. So after EK algorithm, we realized that, well, the slowest part about EK is finding the shortest path before finding the shortest path every time before verifying whether it's an increased flow path. And why do we have to find the shortest path every time? Because after we realized a path is full in its capacity, for example, this pipe after the first increased flow, it's reached this full capacity, we'll delete this path, delete this edge from the graph, and now we have to find the shortest path again. So we have to run the shortest path algorithm every single time, and that is very slow. So the Dinic algorithm, which has time complexity of merely n squared m, is basically find the shortest path once, and then we do the increased flow operation a few times. And at this point in the video, if you really understood Webflow, you might still have a few questions about how exactly this increased flowing operation really works. And we've only been talking about forward edges with this, and how does backward edges go. So now we're going to explain all of them along with the process of Dinic algorithm. So this is my template for Dinic. As you can see, I added a bunch of comments, and it's exactly 200 lines. Yeah, I haven't seen one of those in a while. Anyways, yeah, Webflow Dinic template. So we're just going to go through my code. Let's start with the main function, just as always. N and M is number of edges and number of nodes. I mean, reverse. This is number of nodes, this is number of edges. S is the source, and T is the terminal. We input every single edge. This is an edge from X to Y with a flow with a capacity of Z, and then we push back X, Z, and we have to push back an XID and YID along with it. So basically, first of all, I have to clarify. A lot of you guys might use the other way of building edges. I'm not exactly sure how it's called in English. Hold up. Chain forward star? What the heck? Okay, it is actually chain forward start in English. How literal. Okay, so maybe some of you guys use the chain forward start algorithm to store edges, and well, I mean it's faster and it's a lot less memory, but it's too complicated to write, and you have to write the get head function and a bunch of that stuff, funny business. So I just use good old vector. However, with vector, there is a little problem in which you have to store the ID of the reverse edge in order to do some mysterious operations that we'll mention later. So yeah, so ID is just whichever edge in Y. So for X, when you look at EX, you can just look for XID in Y, and you'll be able to know the reverse edge of this EXI edge. And yeah, you'll understand later. Right now, we haven't used this, so you're probably like 99% confused, but you'll understand later. And then we run Dinic. Dinic algorithm is pretty simple. We just do BFS each time. BFS is finding the shortest path, and we can use BFS and don't have to use Dijkstra or other algorithm because, well, it's non-weighted graph, and every single edge has a weight of 1. And then we continuously trying to find the increased flow path by using a DFS algorithm. So first of all, let's take a look at the BFS and see how we find the shortest path among this very complicated graph. So BFS is just like any other BFS, except we add one more constraint in which an edge can only be used if the flow is still greater than 0. So I.flow, so I made a struct and it's an edge, and obviously it has a flow that has an ID, which is a reverse edge, and then it has a destination, just like any other vector stored edge. Except this time the flow is a variable, and every time you increase the flow of this edge by 1, you decrease the variable by 1. So I.flow means how much flow is left in this edge. And if the flow is greater than 0, that means we can use this edge, otherwise we can't. And then everything else is just like BFS. Except another minor optimization is cur.I, which means currently which edge we've gotten through on I, because obviously every node is going to have a lot of outward edges, and we don't want to have to reiterate every single one of them. So say we have 10 edges, and now we're at the 5th one, and then the DFS took us to some other function. We have to, when we come back to this node, we can use the cur to make sure we don't go through the edges that we've already been through. So here we're just initializing that, and you'll understand how we use it later. And then finally, if the distance to t is -1, which means we can't reach t anymore, that means there isn't another path that is not filled anymore, and then there is no other increased flow path. So we're done. Return 0. And now is DFS time. So basically, the difference between EK and Dinic is the fact that in Dinic we use a DFS and do the increased flow operation on multiple paths after a single BFS, instead of like EK, in which one BFS only make us verify increased flow path on one path. Anyways, yeah, so we're currently at X with the flow currently coming into X being flow. So this is the amount of flow coming into X. However, do know that the difference between the total flow into X and current flow into X is not the same thing, because right now we're basically ignoring all the previous flows as we're already shrank the size of the edge accordingly. So we don't even have to worry about it, right? Because every time we increase the flow of edge I by 1, we decrease I.flow by 1. So we don't even have to consider the previous flows. Okay, so if X is t, obviously we've already reached it and we don't have to increase flow anymore, and we just return flow. That is the maximum flow that we can increase on this increased flow path. And if the sum is not 0, the total flow increase this round from all the different it's called augmenting path. It's not increased flow path. I'm such an idiot. I forgot. Anyways, yeah. So the total flow increase in this round from all augmenting path right now is 0. Now we go through every single edge, and now you see why we need cur. We start from cur, so we don't have to go through every single outward edge of X. Y is obviously Y, and then distance of Y is the thing that we found in BFS. We have to make sure that Y is the next node in this BFS process in the shortest path. So if this is true, that means the next point after X in the shortest path is indeed Y, because, well, obviously there's an edge from X to Y, and this Y is equal to this X plus 1, obviously. Okay, and we have to make sure that this edge has a flow of more than 0. That is the only possibility that it can be an augmenting path. Y is the next point after X on the shortest path, and there's still flow on this edge. Yup, okay. Alright. Anyways, yeah. Now is the amount of flow increased. Obviously, we do DFS again, and DFS will only return when we reach T, and so this will return the... Hold up. Okay, yeah. Will not only return when it's T. This thing will return the sum of all the increased flow on all augmenting paths starting from X. So we have to make sure that the flow we return is less than the flow that our sun and every other later point on the path from X to T can take. So if right now the flow is greater than, if right now the flow is greater than now, which is the flow that our every single sun on the path from X to T can take, then we have to decrease the flow by now. So, hold up. Oh, okay, sorry, I misunderstood what I wrote here. Okay, I wrote this code a while ago. Now is the amount of flow increased, and we take the min over here, not outside the DFS, but inside the DFS. So basically, the amount of flow that we give from X to Y is either flow, which is the amount of flow that X received, or EXI.flow, which is the amount of flow that X can still give out through this edge from X to Y. So we DFS that, find the total amount that we can save, or we can increase, augment, whatever you want to call it, and then we subtract the still available flow by now, because, well, obviously we just took another flow with now units through the same pipe or edge, and the available flow left for us to use is decreased by now. Now, this thing is added by now because the reverse edge of this current edge. So basically, okay, the smart thing about the Dinic algorithm is that is the part I haven't talked about. This is why we need the XID and YID, remember from earlier. So the smart part about Dinic algorithm is the fact that we built a reverse edge for every single edge. It's just that the only difference between the real edge and the fake reverse edge that we've built is that the real edge started with a flow and the reverse edge didn't start with a flow. So this is going to be kind of hard to understand, like, why would we make an imaginary fake reverse edge for every edge? Well, this actually makes a lot of sense because, well, first of all, allow us to process the forward edge and backward edge with the same operations without having the special check. And second of all, this is actually really related to how we can augment using a backward edge. Essentially, long story short, if a backward edge has a flow of greater than 0, we can augment. And every single backward edge has to have a flow of 0 at the end of all augmenting. And if you're interested in that, since this code is going to be posted down in the comments, you can read this entire section of comment that I made, line 98 to 143. Or I'll just read it real quick right now. Okay, now this is quite difficult to understand, so allow me to explain the cancellation operation. Basically, we can cancel some flow on a certain edge that we obtained from the earlier augmentation to achieve an increase on the total flow, and this is why we need the backward edges. Basically, changing from decrease the flow from X to Y on the edge X to Y on the edge XY to increasing the flow from Y to X on the imaginary edge that runs from Y to X. But how we're doing so increase the total flow? Well, to explain that, let's say that we're currently at a backward edge, meaning that edge I from X to Y actually does not exist. Instead, there's only an edge from Y to X, and on an earlier augmentation in a different DFS, we increase the total flow by EXI.flow. So edge I as the backward edge is added by EXI.flow, obviously, right? Because we added it up here. It's added by EXI.flow. And now, the only reason why this edge is on the shortest path this time during the BFS is that, right? Because we added it. Now we're at I, and we found that going from Y, there's a path of flow. Now we know that's because we did DFSY. And so now we want to do a little redistributing of flow. We decrease the flow to the original edge, the backward edge of I, by now is a variable, and let the flow go through the path that we discovered by DFSY instead. So now we have a flow of now missing from the old path from X to T, and we found an early augmentation. So we need to somehow fill that gap up, and guess what? The flow we have right now, the one that we got from S to X, can definitely do that because we know this value must be greater than or equal to now, right? Obviously. Okay, so that is how we increase the total flow from S to T by now. And and why we need to build a backward edge and increase this remaining flow by now each time. So we can do the cancellation, increase backwards flow, which is basically a decrease in the forward flow. Yeah, and then the total flow is decreased by now because, well, obviously you already used now of these flows on the edge from x to y, and then all the edges from x to other node, now you have to decrease the flow by now. And then the sum, which is the total flow augmented, is added by now, obviously. And if the flow is less than or equal to 0, well, there's nothing else to do because all the flow that you got from the father of x is used up. And next time we don't want to go through this path, which is already augmented. And you can read this in giant part if you want, and I'm not going to. Anyways, finally, this is basically the process of the Dinic maximum flow minimum cut algorithm. And notice that since maximum flow is equal to minimum cut, this algorithm also finds the minimum cut of a graph. And this is actually the most powerful part about Webflow. Webflow, usually like 90% of the time when you model with Webflow, you are using the minimum cut. And we'll explain how to exactly use Webflow in a later video. So this is it for this video, and thank you so much for watching. If you actually watch this long, lengthy thing with a bunch of mistakes and probably flaws and algorithms and even coding, and probably someone can hack this with like a bunch of zeros or whatever in the test case or whatever. Okay, I'll see you tomorrow.